Okay, so first let me give some kind of an overview of what we are going to do in this course. I mean, what's the topic, right? There are like these, if you remember, there are these four forces of nature. We don't know much about them, especially this weak force and the strong force. We know that they are acting within the nucleus of an atom. And so as a result, they have a very short range, which means that in our daily lives, we don't experience these forces, right? So they are not even within an atom, they are within the nucleus of an atom. And so as a result, everything that we see around us, like the chemistry and I don't know, the biology and the other physical things that we see around us, it's basically the result of this electromagnetic force and the gravitational force. We have seen what the gravitational force is and what's the basic laws that govern the gravitational force in the previous semester. It's the Newton's law of gravity that handles this. So as a result, the only missing force that we have to go through is the electromagnetic force. All right, that's the reason why we are studying this. And it's not just that course. In the third year, you are going to take 2 more courses. And things like the optics courses that you are going to take in several different courses, for example, in this program, optics is also some kind of electromagnetism, right? It's not some kind, right? Light is essentially an electromagnetic wave. So as a result, you can think that, well, more or less all the, I mean, a great many part of the physics courses are actually about electromagnetism, right? Plasma physics and things like that. I'm not even counting those, right? So electromagnetic force is an important force that shapes everything around us. So that's the reason why. So that's just an old thing. So it appears that there are actually 2 forces in here. When we say electromagnetic force, there's this electric force and something called the magnetic force. So at the end, I'm going to say that the electric force is the force between 2 charges, and the magnetic force is the force between 2 moving charges, right? So that's one point of view. One point of view, sorry, I have to think clearly here, that we can use to describe these forces. In any case, at first sight, we are going to explain this as if these are different forces, right? In the first half of the course, we will be talking about the electric phenomena. We are not going to mention anything about magnetism. In the second half of the course, we are going to talk about magnetism, and we won't introduce the electric fields into the picture in there. Towards the end of the semester, we are going to see that, well, these 2 forces are actually somehow intimately related with each other. And that's the reason why we just call this, I mean, we don't distinguish between these 2 forces. We actually call them as just electromagnetic force, right? But as I said, I mean, when you're starting learning these, it's probably best to start learning the electric force first, then go to the magnetic force, and then at the end, we are going to unify them. So these are like the different places where I think, yeah, the things are made up of atoms, and atoms somehow contain charges. And so therefore, the interaction of the atoms with everything else is basically an electromagnetic interaction. All right, I think there are some examples of, like that in here. So I'm not going to go into some of the unnecessary details in here. All right, so that's the molecule. To keep the molecule intact, some electric forces should be applied. It's basically the forces between the electrons and the protons, right? So there's also a force between 2 electrons as well. They repel each other. The protons also repel each other. But there are some attractive forces between unlike charges, and this is the one that somehow keeps them together. And it's not just the forces that actually keep a molecule together. to keep different molecules together, we also have to have some forces between molecules, and these are also all electromagnetic forces, right? They actually take special names like the hydrogen bond and the van der Waals forces and things like that, but they are, these cohesive forces are actually all electromagnetic in origin. And the surface tension and capillarity and the contact forces that we have seen in the previous semester, like the normal force, the friction force, the tension force, and things like that, right? They are all electromagnetic, and they are also magnetic forces as well. Light itself is an electromagnetic wave, but that's too much for us. I think in the last lecture, we are going to see something about light. And there are some certain courses in physics in this department that we are going to take, which is about these electromagnetism. All right, this is somewhat a crude map of what we are going to do, right? First of all, we are going to start with what we call as the electrostatics. In that case, the charges are at rest, they are not moving, so that means that there won't be any magnetic force involved. Charges are at rest, they are going to produce electric fields, and the electric fields would not be changing with time too. So that's something called electrostatics. Right, it's like, I don't know, 4 or 5 chapters with these. Then we are going to start describing the electric current, and circuits are somewhat included in it. And after that, we are going to pass to magnetostatics. So this is just like electrostatics, but we will be talking about the currents which are not changing with time, all right? So there will be some currents in that circuit, and we are going to talk about the magnetic fields produced by them. And the magnetic field would also not be changing. So that's more or less towards the end of the semester. And at some point, we are going to talk about the magnetic induction. So we are going to see that if somehow the magnetic field in a region changes with time, then an electric field is produced. So that's called an induced electric field, and this phenomenon is called magnetic induction. And then at the end, we are going to see the opposite of this one, opposite effect. We will show that if an electric field changes with time, then that's going to produce a magnetic field. And so as a result, with these 2 chapters, we are going to combine them and then talk about this electromagnetism in general. Okay. All right, so that's the end here. Do you have any questions about these? Just a very quick summary. Let's see, what else? And then I need to talk about the electric charge. All right. So I'm going to do this again quickly. All right, this is going to be our first equation, basically the force between 2 particles with charges, right? So the charges are Q1 and Q2. The force between them is shown by F. So the forces are equal and opposite, so consistent with Newton's third law, obviously. And the force expression is given by the Coulomb's law, right? At this point, just like in every physical law that we have seen up to now, we're not going to try to deduce this from simpler equations or simpler relationships, because this is the first fact that we start with, right? So somehow Coulomb has a way of measuring charges, has a way of measuring the force applied between 2 charged particles, 2 charged objects. And he somehow deduced that the force between them depends on the distance by the inverse square law. And then he has written down this law in here, right? So we are not going to question this. So we are going to accept it as it is. And then we are going to deduce its implications. All right? So what are the implications of the Coulomb's law? So the first chapter is essentially like that, right? So the chapter 21. We will be basically talking about the electric fields produced by the field concept produced by continuous charge distributions. And towards the end of the chapter, we talked about the dipole moments, dipoles and dipole moments. Okay, so in any case, but since we introduced these kind of things, we have these new concepts like the charge. So this Q1 and Q2 in here, sorry about that. So we have to introduce a unit for them. So the fundamental unit is the Coulomb unit. So together with this, I mean, in mechanics, we have seen three fundamental units: the mass, length, and the time units. So here with this chapter, with this semester, we are adding the Coulomb as the fourth fundamental unit, actually. There are three other SI units that people define, but these are somewhat irrelevant. They're not really necessary. So we can express everything in nature in terms of these four fundamental units, right? Just keep this in mind. So we are going to also define new units like volts and ohms and things like that within this semester. All of them are somewhat derived units of involving coulombs, right? So as a result, we are going to see lots of units in here. So the question is like, what is charge in that concept? And I mean, in this equation, what is charge? All right. Perhaps it is nice to think about what the meaning of that is. But I'm just going to quickly give the answer in here. It essentially is something that we call as a coupling constant, right? The basic idea is that the particles can interact with each other through many different ways. They can interact, for example, through gravitational force, or they can interact with strong force, for example, or weak force, and with electromagnetic force, right? So the charge of a particle is essentially the coupling constant that tells us how strongly that particle interacts through electromagnetic force, right? So there are these particles without any charge, like the photon, for example, or, all right, forget about photon. For example, neutron, so it has zero charge. That means that it doesn't interact through this electromagnetic interactions, right? So any particle with zero charge, with charge zero, means that it doesn't interact. If it has a charge, like an electron or a proton, for example, then they interact with each other through this electromagnetic force. If the charge is double, then it interacts twice more strongly with that force, and things like that, right? So in that respect, it's a property of the particle that tells us how strongly it interacts with other particles through that force. Okay. There's a question probably, will it always be defined like that and never individually? I don't know what you mean by this, but charge essentially tells us how that electromagnetic medium is kind of used. So as a result, a moving charge, for example, is going to produce a magnetic field, but if there's no charge, then that means like it won't be able to produce a magnetic field. So it has no way of actually interacting with these fields. Even if there is nothing to interact, can we still define it? I think we can ask this question. Yeah, well, the answer is yes, because I'm going to change the concept actually, right? So in a moment, I'm going to talk about this. Instead of talking about the two particles interacting with, I'll be basically talking about a particle interacting with a field actually, but I'll try to describe this in a moment. All right, that's what I have said, right? Measured by interacting with the object. Charge Q1 is measured by interacting with the object. So if that's a property, then the only way to measure that property is to somehow apply an electromagnetic force to it. So the Coulomb is the unit, so it's one of the base units of the SI system. And there are many derived units like amperes, volts, and Teslas, and Farads, and things like that. So we are going to, I don't know, at least around 10 new units in the semester. So one property is that it is conserved. So that means like if you have some kind of a closed region, meaning that there is no particle exchange with the outside. So the particles cannot enter or exit your system, but perhaps energy can enter. In any case, the total charge within the system should be constant, right? It should always be the same. I don't know, there are examples like, for example, neutron decay, for example. Neutron does not have any charge, but in a decay, it just produces a proton and an electron, so they have equal and opposite charges, so their total charge is equal to 0 all the time. So as a result, the charge conservation is something that's important. And the question is, why is it conserved, right? This is not a question that we can answer within this course, but this is one of the important things, right? So in the previous semester, probably I have told you about this Noether's theorem, discovered by Emil Noether. Noether actually has shown that if your physical system has some kind of continuous symmetry, actually, then that system has a conservation law. And somehow we can explain all the conservation laws that we have seen in terms of these symmetries. And symmetry essentially means that if you change something in your system, the physics doesn't change. So, for example, there's a time translation symmetry which says that the laws of physics does not change with time. So F equals ma was F equals ma in Newton's time, and still the same in here. So this somehow, by using different mathematical arguments, we can show that this is related to the conservation of energy, for example. Right, so space translation symmetry is related to the conservation of linear momentum. Since we have like 3 different directions in space, like X, Y, and Z, we have 3 different conservation laws, actually. The X component of linear momentum, Y component, and Z component, for example. In any case, so the rotational symmetry is related to the conservation of angular momentum, and there has to be some kind of a symmetry related with the conservation of charge. Okay, so the problem in here is that, yes, there is a symmetry in there, but it's complicated, right? It's not really a symmetry of nature. It's a symmetry of the mathematics that we use to describe the nature, right? It's not, it's not a symmetry on the nature side, it's the symmetry on the mathematics side. Right? It's called the gauge symmetry. This is basically somewhat related with the fact that, for example, we can add a constant to a potential energy, for example, because only the changes in the potential energy is important physically. So this is some kind of a mathematical symmetry of the concept of potential energy, for example. The gauge symmetry is basically related to this. So it's quite complicated when you take particle physics, quantum physics, actually. Perhaps they are going to talk about the symmetry, but that's something else. Then there is this property that the charge is quantized. So that essentially says that the charge of the proton is exactly equal to the charge of the electron with an opposite sign, right? They have exactly equal charges, but with opposite signs. This means that the charge of any neutral thing, like a neutron, for example, or a hydrogen atom, is exactly 0. That's the same thing as saying that. Or saying that all particles have charges which are just integer multiples of that fundamental charge unit. Okay. So experimentally, we don't know if this is really the case, right? We don't know if the proton's charge is exactly equal to the electron's charge, because charge measurement always involves some kind of error in it. And if there's an error in it, then you can never show that these are really equal to each other experimentally, right? But of course, if there is a difference between them, we know that this difference is extremely small, right? This is some of the modern experiments can actually set a bound on it. So as a result, people do not have any suspicion about whether charge is quantized or not. So it appears that it is quantized. And again, the same question, why is it quantized? Again, this is one of the fundamental questions that we don't know the answer to this one yet, right? There has to be some kind of a reason for it, but we don't know the reason for it. So quarks and yeah, whatever. All right, so that's the end of this thing as well. So it's just a summary of the charges. Okay, I don't know if you have any questions for these. Okay, I need to close this. All right, so I'm going to therefore start with this. Sorry about this. Let me go back to this. Sorry. I think I'm going to open. I'm going to open a browser and then I'm going to log into the AutoClass. So sorry about this. Yeah, okay. So let me tell you about these some previous year's videos. So I'm going to mostly refer you to these videos, all right? But for some reason, I cannot connect it. I cannot connect. In any case, all right. All right, so there are several past videos in here, right? This is basically this one is from the first year that we have this COVID situation, but we have actually covered like the first 4 chapters of the course, and then after that we have entered into this situation. So as a result, the topics in here starts from the chapter 25, but these are essentially topics which are not lectures really, but these are kind of specific topics within each chapter, all right? So as a result, you can look at them. This is one of the things that I should actually tell you. And the other one is this one. This one is essentially is a whole complete chapter. There are lecture notes in here with this kind of names like that, starting with P110 and things like that. So there are also dates in here. They are also ordered. But in addition to that, there are some videos like these, right? I don't know, a quick reminder about vectors. So these are basically explanation of some topics in some condensed form, perhaps, and some of them involve some problem solutions, like a short thin rod, for example, in here. And I think one of them is even shorter in here. I don't know which one is short. Yeah, this one is shorter than that one. So there's a lengthy explanation in here and a shorter explanation in here. So probably this means Q means like quick in here, okay? So in any case, I'm going to refer you to these videos most of the time. And in here, in these online lectures, I'll be basically talking about some kind of a summary. Okay? So as a result, just keep this in mind, right? So as a result, I'm just going to repeat some of the concepts in here, but I'm not going to be able to solve a problem like that, right? So since all of these problems have already been solved and is placed on YouTube, I'm just going to just give a short explanation in here, okay? So in here, we are going to start with the Coulomb's law. So we have 2 charged particles. Charges are basically properties, some properties of these particles, like mass, for example. Let's just keep this in mind. And so they apply a force to each other. So I'm going to use a green color for the forces, for example. All right, they apply a force to each other. So these forces are equal in magnitude and opposite in direction. So let's say that R is the distance between them. So the Coulomb's law says that the force between them is a constant multiplied with the charges of these particles divided by R squared. Okay, there are a few things that I need to change in here. So the first one is that this coefficient in here, because of some reason that I'm going to explain later in the second chapter, instead of KE, we just use this expression here. We just write this as 1/4 pi epsilon 0, where this epsilon 0 is called the permittivity of the empty space. Permittivity of the empty space. All right? Or some people call this as vacuum, right? What is permittivity? Well, it's just a name, all right? So perhaps there's some kind of an English meaning of that word, but that's not important for us. So do not try to give any excessive meaning to that expression here. So it's just a constant of nature with some certain units, and people just call that constant as permittivity, all right? So we are going to define a corresponding permeability of space as well for magnetic force as well. But I mean, here we are just going to call this as permittivity. Okay, so we say that this is the permittivity of empty space, which means that if these two charges are inside a medium, for example, inside some kind of a semiconductor, for example, right? So instead of empty space, these two charges are inside a semiconductor. In that case, what happens is that this force expression is still valid, except that instead of this epsilon 0, we have to use the permittivity of that material, of that medium. Okay, so it's that kind of an advantage in there. And we basically describe the effect of the medium through their permittivity values. All right, again, we are going to say something more about this, I think in the third chapter or the fourth chapter in the semester. All right, so that's the first expression that we are going to use, right? And the second thing is, well, let's just remember that the force is a vector. All right, so but this only gives us the magnitude of the force. Somehow we have to write down a formula that somehow includes the direction as well. In that case, this is the formalism that I'm going to use, right? I'm going to, for example, what I'm going to do is something like that. I'm going to place or choose an origin at the location of one of the charges. And in that case, the other charge has some kind of a position, right? So that's a position vector. It's essentially a relative position, right? So this position vector, if you remember, I can use a unit vector notation for that, right? It has an x component, y component, and a z component. And I can, well, basically, the radial distance between these two charges is essentially the length of that vector. And so as a result, this is the magnitude of that vector, right? But we usually call this as the radial coordinate or the radial distance. Okay. In any case, so in some problems, that radial distance actually can be taken as some kind of a coordinate, right? But it's not like a Cartesian coordinate. It's some kind of some other kind of a coordinate actually. So x, y, z, these are Cartesian coordinates, and r is some kind of it's actually called a spherical coordinate, right? So it's something that we are going to see later. But think of this as like a coordinate, right? R is some kind of a coordinate. But just like the x, y, and z coordinates, where we actually have a unit vector along this coordinate direction. So, for example, our unit vector is the unit vector along the x-axis, and so on. Similar to that coordinate, I'm going to define a unit vector along that direction. So this is the radial unit vector. So r hat is the something that I call as the radial unit vector. Okay, so that's the unit vector along the direction in which r increases. Okay, so that's the same thing as well. This is just like the I unit vector, for example. So that's the unit vector in which, sorry, let's say unit vector along which x increases, right? The x coordinate increases along this direction, and so therefore the I unit vector is along that direction, or some people call this as the x hat, for example, right? In any case, so the radial unit vector is like that. So at a point is the unit vector that gives us the direction in which the this radial coordinate increases. Okay, the problem, the distinction, sorry. In that respect, the radial unit vector is similar to these Cartesian unit vectors. However, the radial unit vector depends on which point you are on. So at this point, for example, the radial unit vector will be like that. At that point, the radial unit vector will be like this, and so on. So as a result, it's a unit vector that depends on which point you are using, right? That's essentially the only complicated aspect of the radial unit vector, right? Here you can see that this can actually be written as the radial unit vector is the position divided by its magnitude. Okay, so as a result, you can easily see it like this. In any case, I'm going to draw this thing again. Sorry about that. So the same story again, all right? So x, y, z axis, but I'm not going to label them. So one of the charges at the origin, we have the other charge in here. R is the radial distance, and r hat is the radial unit vector. In that case, the force applied on this second particle, right, let me also write down the charge in here. So F2 is given as 1/4 pi epsilon 0 times Q1, Q2 divided by R squared times the R unit vector. So this is the correct vectorial form of this the Coulomb's law. So that's the force on particle with charge Q2. So why do we do this? Because it simplifies some certain things. Because, I mean, when we talk about the electric force and things like that, we are going to have situations where we have to add up these forces. So we won't have a single particle, we have many particles, sometimes infinitely many, and we have to add up the forces applied by such particles. And so as a result, since the forces are added up vectorially, we need a vector expression. What is nice in here is that in here, then if you use this equation, then you don't have to consider whether the charges are like charges or unlike charges. So somehow this formula also gives you the correct direction. So for like charges, like if both charges are positive or both of them are negative, so in that case, Q1, Q2 product is positive. So in that case, F and R are parallel to each other, right? F and R are parallel. So that's a situation where the R unit vector and the force vector, they are in the same direction. So the force is repulsive. Okay, so this is for like charges. For unlike charges, the product of Q1 and Q2 is negative because one of them is negative and the other one is positive. In this case, this formula tells us that force is actually a negative number multiplied with the R unit vector, which then implies that the F and R are anti-parallel. So as a result, R is along this direction and F is along that direction. Sorry about this. So R unit vector is along that direction. So I need to draw this consistently with the picture. So the force is like that. So they are anti-parallel. So that means that the force is attractive. Okay. So in the ordinary expression of the Coulomb's law, we say that, well, yeah, the force has this magnitude and the force is attractive if the charges are unlike charges and so on, right? We just express the direction of the force explicitly. However, if I use this formula, then I don't need to write down the, I don't need to describe whether the charges are like charges or unlike charges or the force is repulsive or attractive. So somehow this force expression produces the correct force. Okay. Okay, so let me quickly do this. So in any case, if I have a charge little q in here, but charges, let's say Q1, Q2, and so on in here, like lots of charges in here, if I want to compute the total force, total electric force acting on this little q charge, so let's say it like this. This is F net. So that force can be written as like 1/4 pi epsilon 0 Q1 times little q divided by some distance squared times the some unit vector plus I mean the other expressions. Right? So, let me quickly write them down and then I'm going to explain why I'm doing this. Right? In any case, in all of these expressions, you just notice that the charge of the particle that you're considering here is common in all of these terms, right? So that means I can write this expression as force expression as Q multiplied with something else in here, right? So that something else is called the electric field, right? So here E is, we just call this as the electric field due to particles, let's say due to other particles with charges Q1, Q2, and so on. All right. So in any case, for this kind of a situation, therefore, instead of dealing with forces, it's kind of easier to deal with electric fields, basically. So as a result, for every position, every location where we can place a charge at, we are going to claim that there is an electric field produced there. And this electric field is due to all the other charges and not that particular charge, all right? And so this concept is going to be useful for everything, actually, right? So in that case, we don't have to deal with the forces. We have to deal with the electric fields. All right, so in here, let me just stop here. But as I said, I mean, this is not enough actually. So either on Saturday, on Sunday evening, towards the evening perhaps, I'm going to announce another lecture. It's just really going to be a summary actually. But first I'm going to explain why electric field in here. Why do we need to use electric field? Because it has some nice features. And then after that, I'm going to describe these two situations where two kinds of problems that we actually concentrate on in this chapter. One is the computing the electric field produced by a continuous charge distribution. And the other one is the concept of electric dipoles, right? But let's just stop here. And I'm not going to do a second hour today, right? So let me stop the recording. Sorry, let me first do it like this. Stop share and then stop recording.